Okay, good afternoon, everyone. I'm assuming everyone who is attending in person has uploaded the campus pass. So I'm checking online and I'm looking at it again. It takes a while for me to go through the quarter and put names to faces, and especially hard in the pandemic when everybody's masked up, But students, some of you are familiar to me. Some of you have taken my class previously. You've stopped by my office, so I'm familiar with several of you. But again, I will check the campus passes, before class as and when I have time, but it's an honor system here. Just want to make sure that everybody is, uploading their campus pass. All right. The other upload we are going to do today, well, for the first few minutes of this class, is just practicing the scan and upload. So there should be some equation sheets. They are, well, I'm going to use it for both of my classes. This is actually says 201. It does not really matter right now. I'm just passing around these blank equation sheets. What I want students to do is use any scanning software, just one page. It's just one page. You can just pass them around. Oh. So, and students who are at home or watching online, just take any standard letter size piece of paper that you have, any past assignment, even a blank sheet would do. So at least what I want students to do is scan at least like 2 pages. So if you're in person, you have the equation sheet. All you're going to do is you're going to scan the front and the back, create a single PDF file, and you're going to upload it right here. Let me bring up quiz 0. That will all come later. Today is just practice. So every Canvas course, every course has its own Canvas website. What I want to do is I want to ensure that our website does not have any glitches. Okay. Now, students have been doing this for the last year and a half, so everybody's familiar with scanning and uploading assignments. But I do not want there to be any surprises next week when we actually get to our first week. And so that's the purpose of this small exercise. This is actually listed as quiz 0. I'm going to bring it up right now. So if you go to assignments, 321.04. Actually, it does not matter because it's going to be uploaded from inside the student's login. And so, yeah, naming does not matter. Just make sure that the page has your name on it. Okay. So right now it's fine. It's okay. Just scan and upload. But when it comes time for quizzes and everything, the document, just in case if you need to print or the grader needs to print it, then we want to make sure that your name is on there. Yes. What do you mean? You mean it's not scanning properly, or if there are issues? You mean? Well, we'll be in person, so just let me know what's going on. Too bright is not a problem. Too dark is always a problem. Nah, we'll see. Too dark Professor is more common rather than too light. So online students, do you have any questions?
Yeah. Can you hear me?
Go ahead.
Oh yeah. So we can just upload like front and back of like any assignment?
Yeah. Any assignment, okay, cool. Even if it's a blank page, it's fine.
Okay.
I just want to make sure that the students' logins and the Canvas website are linked correctly, and everything makes its way to my end. And so that is the purpose of this little exercise. Again, taking the quiz online is not an option right now. It'll be a little well, not a little, a lot hard for me to actually proctor in person and then online separately. And so online option is only if a student cannot attend class in person due to medical reasons accompanied by a valid medical note. Yeah. Yeah, again, just make sure it's not separate. It's one single file, at least 2 pages, because that's what's going to be most of the quizzes are going to be like 1 or 2 pages. So front and back.
So that's actually so for example for all these quiz we need to that one time we still need to take photos for that
Yeah,
even if we're in person.
yes, even in person. So the purpose is so that there's no delay in handing over the quizzes to the grader. I mean, the grader, if they don't have time to come see me on Friday afternoons, then we'd have to wait till Monday to, for them to collect it from me, and then just keep getting delayed and delayed. So this way it's better. It's already online. If the grader wants to get the job done on Saturday or Sunday, you already have the results by Monday, right? And so it's a more efficient way of, getting things done.
Also, you're going to receive the hard copy or do we still need to keep the hard
Haven't decided what to do. I'll let students keep the hard copies, I think, as of now. So with regards to quiz one, since we are still talking about the concepts, we'll get into a little bit of analysis today. And then, the first homework is not yet posted. So I have decided to not have the quiz on Monday, but we'll have the quiz on Wednesday instead. Okay, so we'll go over a little bit of analysis. We'll look at some ideal diode models, some examples, load line analysis, and then I will assign homework. You'll have until Tuesday night to get their homework done, and then Wednesday we'll have the quiz. Sounds good?
Okay.
All right. Yes, question?
You have to credit the Monday then?
The extra credit is more for like practice. So more for like practice, students to catch up if they have taken the course like, more than 1 quarter ago, or whether you take it 1 quarter ago or not, and the assignment's going to stay there. It's not going to disappear. But again, it's extra work for students who want to get like a refresher. So that's why there are a lot of problems in there.
That one also gives you the grade points, like,
Yeah, so the extra credit points will be carried forward towards the entire homework assignment and towards the entire overall course grade.
oh yeah, it wasn't like the refresher counts, but it does.
Yeah. No, I will open it up sometime today, later this evening. Yeah. Yeah. All right. Any other questions? Okay. All right. Let's get started. Oh, someone asked me about PDF files for the website. So I posted the PDF file right before class. So if you want to download the PDF files and make your own notes or annotations, it's available on the website. Huh? No, it is on the class notebook also.
Okay.
Yeah. So on the Canvas page, if you go home, slides. So slides 1 through 26 are now available. So I'm making a lot of changes, trying to update the material. And so, the slides that I had previously, I'm making a few changes, updating some of the problems, some of the concepts, and making it easier, to explain and understand. And so that's why I'll be posting it as we go along. And then, of course, class notebook. Class notebook also has those slides. Let me see. Hopefully they should have synced. Yeah. The class notebook also has slides all the way up to 26, right? So it's the exact same thing. Okay. So students can access the class material in, in a couple of different ways. Actually, more than 2 different ways. Okay. So we studied, not studied, but we discussed semiconductor materials, and we saw how we can create 2 different kinds of materials, semiconducting materials, from a single piece of silicon or germanium or whatever semiconductor we are using, right? Depending on the impurity, whether it is from column 3 or column 5 of the periodic table, meaning it has one less electron or one extra electron compared to silicon, we can have a negatively charged material or a positively charged material. And so depending on the number of free carriers we have, meaning if the resulting material has a lot of excess electrons, then we say we have a N-type material or N-type semiconductor. Yes. Thank you for reminding me that. Yes, I am recording. Thank you. I know I'm laughing and several of you are laughing, but that's a very good reminder. Yes. Yes. So even if you're watching online, yeah, do not forget to remind me. It usually does not happen that often. I don't think I missed recording all of last quarter. Yeah.
Professor Trotta, we can't see the slide. Should we just like pull them up
Oh.
on the?
All right, let's see. Okay, there you go. Can you see it
Perfect,
now?
thank you. Yep.
Okay, great, thanks. Okay, so as I was saying, so if we dope it with a column 5 material, we have an extra electron. That means there are a lot of free electrons in that semiconductor material. And so it results in a N-type semiconductor or N-type material. And if you dope it with a column 3 material like boron, then we have a lot of excess holes, meaning devoid of electrons. So a lot of extra positive charge or positive carriers. So when I say carriers, these are known as charge carriers, right? Electrons moving in a circuit are they are carrying and transferring charge, which is of course the rate of flow of charge is defined as electric current. So when the electrons move, the holes are moving in the opposite direction. So we call them or refer to them as charge carriers. Okay. So we have P-type material and we have N-type material. Right? Any questions about anything we have talked about so far? Okay. So by themselves, the P and N-type materials are not going to do much good. Okay. But when we bring them into contact, what do we get? We get a PN junction. Okay, when they are brought in close proximity, well, not proximity, they are in contact, physical contact with each other, we get a junction. We get a junction. It is simply known as a PN junction. Okay. So, two types of material, two electrodes. Remember, vacuum tube, diode, two electrodes. So when they built a semiconducting version or semiconductor-based version of that device, they still carried over that name. Okay, so the name comes from the vacuum tube diode, but this solid state version or semiconductor version is also referred to as a diode. That goes to the legacy of that vacuum tube diode or vacuum tube device. And the terminals are also the terminals also have the exact same name. Remember the vacuum tube, we had a cathode and we had an anode. And so those names for those terminals are carried over. And so here, this is the N-type material. This is the P-type material. Guess which one is which? Anyone? Cathode is the, no, it's the other way around. Well, at least one person is speaking up. Everyone else is, I don't know, apprehensive. Maybe I should award her like one bonus point. That's when I have more participation, right? So what was I saying? Oh, yeah. The N-type material is labeled as a cathode. P-type is labeled as the anode, because that is where the electrons will originate. Now, what happens when we bring them into contact? Remember, the goal of the atom is to reach kind of like an equilibrium, right? So you have an electron here and you have an absence of an electron here. It means there's space here. So if it's moving around, what do you think is going to happen? Right? We have a hole here and we have electron here. So this is electron, this is a hole, right? Every electron will try to occupy the space, and will try to recombine. When that electron occupies that empty space or that empty spot, we call it as recombination. Okay. So what happens is you have a negative charge here, you have a positive charge here on the left. Right. When I say here, I'm talking on this N side, you have negative charge, you have positive charge on the left. The electrons from the right side, from the N side, will cross over and recombine with the holes on the left side or the P side of the material. And that means that one negative charge from the right side and one positive charge from the left side disappears. Okay, let me repeat that again. You have an electron on the right side, you have a hole or empty spot on the left side. So minus negative charge here, positive charge on the left, right? Negative charge on this side, positive charges on that side. When you bring them in close contact, these electrons will combine with these holes, meaning physically that electron is going to move into that empty space. That process is known as recombination. And again, it's a whole different branch of physics. I mean, you could spend hours and days talking about it. Yes. Yes. And so it's only in that close proximity. And so you have a negative charge that combines with a positive charge, and both charges disappear. So it's completely devoid of any charge and any charge carriers. Yes.
They always like why they call it or you got shot because of the example that
Yeah. Well, I'm just talking about one, but there'll be several hundreds of thousands of electrons that will actually like cross over and then combine, right? But what happens is there's this region, the shaded region that we see right here. And again, this image is not to scale, obviously. That region is very, 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 very close to the surface or very, very near that junction, right? Now this is like blown up for effect, but in reality, it's a very, very thin slice. It's very, very thin. It's right at the junction itself, okay? And so what happens is that region becomes depleted of all charge carriers. It becomes depleted of all charge carriers. And hence the name depletion region. It becomes depleted of all charge carriers. And if there are no charge carriers, there is nothing to carry the charge, meaning charge cannot flow through, meaning there is no electric current. So it's completely devoid of all charges, and there will be no current flow across that junction. So again, this is the most fundamental of semiconductor concepts, right? This depletion region. This is the diode, the PN junction itself. It's dancing, it's drunk dancing. Oh, come on. Yeah. You gotta file something with the IT department. Let's hope it's now steady. Okay. Is the slide still visible online? The computer is doing weird things here.
Yeah, yeah, we can see
Okay, great,
everything.
thanks. So as I was saying, so this is one of the most fundamental of concepts, depletion region, right? It's devoid of charge carrier. It only happens when you bring a P and N type material together. Okay, when you bring a P and N type material together. Now, do not get too bogged down into the physics of these things, okay? Because if you start to think about this, there are entire textbooks written about just this stuff. I mean, even I have never read all of this. There's so many things you can go deep into. Yes. Yes. Yeah. This is still cathode. That's still anode. Anyway, the point of that is that depletion region requires a certain amount of energy to be overcome, right? So it requires a certain amount of extra voltage that needs to be applied in order for that depletion region to actually shrink. So before the diode can begin conduction of electricity, that depletion region barrier needs to be overcome. And that barrier, in terms of the material, well, it's that barrier voltage is fixed. For silicon, it is around 0.6 to 0.7 volts. For germanium, it is around 0.2 to 0.3 volts. That is an intrinsic material property of that particular semiconductor. Okay. And it's basically saying that it requires that amount of voltage in order for it to turn on. But that's the device physics. Yes. Yes. Yeah. Yeah. And then, yes. So that happens during the manufacturing process. You just manufacture it and then it's just at that point. Yes. Yeah. Good questions. Now, you see that there are positive charges here in the N-type material and negative charges here in the P-type material. Well, all semiconductors have both kind of charges. It is only the majority, which charge carrier is majority that will define that type of material. So in an N-type material, we'll also have it'll have a majority of electrons, right? Majority of electrons. But it also has positive holes, and they are known as the minority carriers. And the opposite is true for a P-type material. In a P-type material, the holes are the majority carriers and the electrons are the minority carriers. Make sense, everyone? Let's take 10 seconds. Think about it. Let me know if you have any questions. And again, this is, it gets deep into like device physics and semiconductor physics, Fermi levels, energy band diagrams, and it's a whole different world out there. Yes. So it's an actual component. I will. These slides, I do not have a actual image, but I can bring it up on the internet. I'll show you. Now, keep in mind, all of these devices that we see in real life, you will not, the silicon chip is going to be like really, really small. You can't even see with the naked eye. You need a microscope. What we'll actually see is basically the package, the encapsulated package, right? So if you ever seen a printed circuit board, we see all these components on there. And everybody has seen like, those black packages which have, the microchips and stuff. That package might be this big, but the actual silicon piece inside it would be smaller than this, like maybe like 2 millimeters by 2 millimeters. So that entire plastic package is that huge because we need to make physical connections with the outside world. But the actual chip inside is very, very small. So it's not visible, without a microscope. So anyway, this is, as going back to one of the questions that someone asked earlier. So this is what happens when you actually manufacture or when you actually physically create the device, right? It's already at this state. Is it? I don't think so. I mean, Jonathan told me it happened last quarter too, right? This pen is just for this tablet though. It's not for the smart board. The smart board, this is supposed to be a smart board, but they told me that they have disconnected the smart board. So it should not be. Is it? They are actually not supposed to write on the whiteboard. They need a special, you need a special marker to do that. To write on this whiteboard. But I was told, I set up an orientation before the quarter in this room. They told me it's disconnected. I don't know. We'll find out. All right, let's leave the pen down there. No, nothing. Oh, come on. This is too much. All right, let's see if I. No, I disconnected the pen and everything. It's still something with the computer. Okay. Any questions? Other questions? Yes. Yeah. So here in the N-type material, we have an excess of electrons or free electrons to carry the charge. And because you have an excess of, so they are present in a majority number. There will still be holes, positively charged carriers because of the absence of electrons in some spots or some places. And so those will be the minority carriers. They are also capable of carrying charge. And so in N-type material, we have a lot of electrons, meaning a lot of negative charge. There's also some positive charge carriers. And so electrons are present in a majority, so they're the majority carriers. Holes or positive charges are present in a minority, and so they're the minority charge carriers. It'll be changed. They'll be, when it's manufactured, it'll reach a state of equilibrium until we apply an external voltage or external field to it. Yes. So here, yeah, so that's going to be the next point. Yes. So what happens is N-type material, we got electrons and majority carriers, holes as minority carriers. P-type is the exact opposite, right? Now, when we get to the depletion region, what happens? In the depletion regions, the electrons are crossing over. So what is left behind the depletion region? Positive holes. And that's why you have these minority carriers dominating the depletion region. And the same thing happens on the left side. Because the holes have recombined with the electrons on the right side, now we have minority carriers, electrons left over in that depletion region on the left side. And that is what causes that barrier. Because now you have positively charged holes in an N-type material. Again, without going into too much further detail, this is, these are all background concepts. The reason I do this is because I think it's critical. Well, I think it's important for students to actually get some basic understanding. But at the same time, I would also say do not get too bogged down into the device physics. Okay, this is about conceptual learning. But there are lots of other things that govern these. There are hundreds of equations on how they move. There's, it affects the type of material we use, the temperature. There's lots of things that affect these PN junctions. So do not get too bogged down into the physics of this, right? There are lots of things, lots of factors that affect. But I want students to get like a basic understanding. We have a N-type material, we have a P-type material. When we bring them into close contact with each other, right at the junction, we have a region that is completely devoid of charge carriers. Hence, it is known as the depletion region. That depletion region will prevent any sort of current conduction through it. So it requires an externally applied voltage to overcome this barrier. And that is the fundamental operating principle of a diode. You would apply a voltage to a diode, but until that barrier is overcome, it will not allow any current to flow through. So as you increase the voltage, it will reach a certain threshold. Once that threshold is crossed, that's when current conduction will happen. So it is a non-linear device. It's a non-linear device. Okay, let's see. Just do it right here. So this is the symbol for a diode. You have an arrowhead with a line at the tip of the arrow that indicates the cathode, that indicates the anode. In real life, this is a real life diode. It is very, very tiny. If you are taking the lab along with this lecture class, E361, in your lab kit, there is a small piece of component. There's actually 4 or 5 of these diodes in your lab kit. Okay, you'll create a bridge rectifier circuit in lab, I think it's lab 2 or lab 3. I can't remember which one. You haven't received the kits? Oh, wow. All the IEEE students are, well, they're way behind them this time, I guess. Or maybe it's supply chain issues. I don't know. I'm not teaching 360 on this quarter, so I'm not that hooked up into the. I have to have a talk with someone about this. Maybe I'll stop using this computer. This is mirrored. It's mirrored and extended. Anyway, this is a real life diode. This is a symbol. This is a real life diode. Okay. Now, actually, I have an image. Let me see if I have it here. Uh-huh. No, that's just a marking. So I'm going to bring up something here. Hold on. No, this the device that you're seeing on the screen, the image that you're seeing is actually very, very small. It's less than 1 centimeters long and just a few millimeters wide. So it's like a cylindrical package, right? It's 1 centimeter. So if you can imagine, the length of this diode is just like less than 1 centimeter. Okay, and it's a round cylindrical package, right? So but just a few millimeters wide, like maybe 2 or 3 millimeters wide. But when you cut open one of these, this is how it should look. Here, let's see. Let's see if I can find it. Ah, there you go. This is actually a piece of diode that's been sliced from the center. That's the gray silver marking that was at one end. That gray silver marking around that cylinder indicates that terminal is the cathode. This is standard accepted standard accepted practice when they're creating or manufacturing diodes. No matter what kind of diode it is always marked with a circular band. Okay, so this particular diode comes from a series of diodes known as 1N4000. So there's a series of diodes that begins with 1N4000. And so the ones that will be in your lab kit is probably like 4001 or 4002. So you get 1N4001, 2, 3, 4, 5, 6. And then here's the rest of the diode. Okay, this is just the external lead, right? The external lead that that we saw. Yes, it's a silicon wafer. So the actual piece of diode is just right here. You can see the mouse moving around. This is the actual diode right there. That's it. Yep. It's very, very small. Wafer fabrication is a whole different field, right? We actually have a clean room on campus. It's in Building 41. And there is a microfab class that we teach every winter. So if you're mechanical, it doesn't matter what field you are in, The class is offered under biomedical engineering, BMed 434, and the lab class is BMed 435. There are 3 lab sections. I'm teaching one of them. My background is microchip fabrication, semiconductor and microchip fabrication. And so this is the kind of thing that we do in that lab. We actually take silicon wafers and we build actual diodes, transistors, and resistors. We also learn about microfluidics in that class. So again, if you reach that junior, senior level where you need like a tech elective, you might want to check that out. Yes. Yes, photolithography. Yeah. Anyway, coming back here, as I was saying, this entire diode, this is just the packaging, right? This is just the packaging. I was saying it's smaller than 1 centimeter, less than 1 centimeter long. It's a completely blown up image, and you can see how small this section is. So it's very, very tiny, very, very small. Okay, it's very, very small. And when they manufacture it, that's when that PN junction is created during manufacturing process. Okay, and again, completely different technology, completely different discussion. Manufacturing is very, very different than designing and circuit analysis. Okay, let's come back to our slide. So this circular band just indicates the cathode. K, anode A. Okay, so the circular band indicates the cathode. It comes from the time when they used it during the time of the vacuum tubes. I actually don't know why they came up with K. It's like saying it's C, right? So if it's C, CA is pronounced as K. Why? It's the English language. I'm sure there's a reason why, but it's not. Yeah. Okay. So as I was saying, when we have a semiconductor device, like a PN junction diode, it has that barrier, and you need an external voltage to be applied in order for that barrier to be overcome. So when we apply an external voltage, we call that as biasing. When we say biasing, we're applying some external constraint on the circuit. External constraint or external voltage on the circuit. Okay, so you would say it's the biasing voltage or the bias voltage or voltage bias. Okay. So if you take a voltage and you apply, if you apply a negative to the p-type material and you apply a positive voltage to the n-type material, what happens? We have the electrons in the n-type material that would be attracted to this positive terminal, and we'd have the holes, positively charged holes, that would get attracted to the negatively charged terminal, the negative terminal, right? So here you'd have electrons, and here you'd have holes, right? So what will happen is that depletion region keeps getting bigger and bigger and bigger and bigger, because you're now pulling away the majority charge carriers away from that junction. So the depletion region keeps getting wider and wider. All of the electrons in that junction are getting attracted to the positive terminal of the battery, and all of the holes are attracted to the negative terminal of that battery. And so the depletion region increases. And no current flows through the circuit. No current flows through the circuit. And so we call that as reverse bias. So in reverse bias, there's absolutely zero current. In reality, there is a small current that will flow through because of the other minority carriers. Okay, and that current is known as the saturation current or the reverse saturation current. So the very, 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 very small current, it is so small that we cannot even measure it with with just regular methods. It's like 10 raised to minus 12, 10 raised to minus 15. Less than nanoamps, picoamps, even femtoamps. So you need specialized equipment to actually measure these kind of small currents. Small reverse saturation current. Okay, very, 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 very small reverse saturation current. And then the exact opposite happens when you connect the positive terminal of a battery to the p-type material and the negative terminal of the battery to the n-type material. And that is where the fun happens. Now you're pushing the holes towards the junction. You're pushing the electrons towards the junction, right? The electrons are being pushed this way. Holes are being pushed this way. And so the depletion region starts shrinking. So the depletion region shrinks. Depletion region shrinks. Oh. The threshold, actually not A. The threshold is overcome. Okay. And once the threshold is overcome, you have free flow of current. Free flow of current. And that, in short, is the operation of a PN junction diode. Okay. When you connect the n-type material to a positive voltage and the p-type end to a negative voltage, then it's a reverse bias. When you connect p-type material to a positive voltage and the n-type material to a negative voltage, then it's forward bias. In forward bias, as the name suggests, current is allowed to move forward. In reverse bias, since it's being reversed, the depletion region extends or expands, and there is no current flow. Yes.
But that's in the forward bias, that is visible, big enough to overcome the barrier.
Yes. Yeah. And again, as I stated, it's different for every different material. So if it's silicon, it's 0.6 to 0.7 volts, depending on manufacturing process. And then for germanium, it's about 0.2 to 0.3 volts. These diodes, again, energy is transferred, right? So when the diode dissipates the energy in the form of heat, well, when the diode receives the energy, it allows the current to flow through, but some of the energy is dissipated as heat, right? Electronics. That's why we have big heat sinks on our CPUs in a computer, because there's billions of transistors like these. But there are certain materials that dissipate energy in the form of light. LEDs, light emitting diodes. The light emitting diodes basically have a slightly higher threshold voltage. So it's like 1.1, 1.2, 1.4 volts. And depending on the material and the doping, the color of the LED can be changed. Okay. I like this valve analogy right here. It's a flapper valve. And the function of a diode, right? Function of a diode is to actually allow current flow in one direction and block the current flow in the other direction. All right, let me leave the pen right here, see what happens. And I have them come out and disconnect the smart board completely. They have not already done so. Okay, so as I was saying, this valve image approximates, it's a very good analogy for a diode, right? If you have fluid flowing in this direction, the valve opens up, allows the fluid to flow through. It requires certain amount of flow or certain amount of pressure first to actually overcome this valve, right? And so that's one reason I like the analogy. So if it's forward bias diode, you apply a certain amount of voltage until the threshold is overcome, then the current starts flowing freely. When it goes in the reverse bias, the fluid's flowing from right to left, then the valve is closed, there's no more current flowing through, right? And so a diode is going to look like this. Also, one note about the diode symbol, right? The diode symbol has an arrowhead, and so basically that's indicating which direction the current would be flowing in. That's a good way to remember, right? So current would flow in the forward bias, but not in reverse bias. And these are the diode VI characteristic. Okay, we say IV characteristics or VI characteristic. It's simply stated, it's a plot of the diode voltage versus the diode current. Okay, diode voltage versus the diode current. So in the forward bias region, we say the diode voltage is positive, right? So on the x-axis, diode voltage VD is positive, going towards the right. And then when we apply it in the reverse bias, we say that the diode voltage is negative. So the reference is always from the cathode to the anode, right? If the anode is higher than the cathode, we say it's positive. If the anode is lower than the cathode, then we say it's negative. Again, positive and negative is just relative for us. Otherwise, we would never be able to balance out all these equations, right? And so this is negative. And this, of course, is not to scale, but this region, the reverse bias region, can go from like tens of volts to even hundreds of volts. There are some diodes that can withstand up to 400 volts in the reverse bias region. It's not going to damage the device. It will still keep working. So, you know, it's not going to like, unless a threshold is reached in the reverse bias region, when the junction completely breaks down, the junction breaks down and you have a whole lot of charge carriers flowing in the opposite direction. Again, that's a discussion for the Zener diodes. We'll leave it for another day. So reverse bias region, it's a very, very small current flow. Again, this is exaggerated for effect because it's very, very small. So this is the reverse saturation current, or the reverse saturation current. And then we have the forward bias diode. Typically, we illustrate the forward bias diode. And if I wanted to exaggerate it, I would say it like this. And for silicon, I would extend it like this. And I would say this is about 0.7 volts. So 0.6 to 0.7, let's say it that way. Okay, for silicon, this remains as 0.6 to 0.7 volts for silicon diodes. So in the forward bias region, you have no conduction until the threshold is reached. And I know it's not exactly, I mean, I'm showing there's some small current here, but not really. And then once that threshold is reached, there's a sharp increase in that current. Now, the forward bias and the reverse bias characteristic might look the same when we actually compare this region right here, where the current increases very sharply. But this curve in the forward bias region still has some slope, whereas this in the reverse bias, after the junction breaks down, is like almost a sharp drop. It's almost like a step. I mean, once that threshold is breached in the reverse bias region, the current just flows like it's just bursting through. Okay, It does not damage the device. There are some diodes that are intentionally operated in the reverse bias, which is basically the Zener diodes that we'll study later in this chapter. Okay. But for the most part, diodes are always operated in the forward bias region. And well, load line analysis, it's already 2 o'clock, so we leave that for like next week. Anyway, we'll end class here today. We'll leave the quiz for like Wednesday. Again, I'll send out details. But for now, as I said, we don't plan on having a quiz on Monday. I'll be available all weekend. If you have any questions, I will post the homework sometime later tonight. And if you need to see me, I'll be available over all weekend over Zoom. All right. So have a good weekend, and I will see you all next week.
Thank you.
Same as resistors.
That different the positive terminal from the diode and goes out. After resistor, I mean resistor, we always put like positive and negative and the current pass through.
Oh, voltage. Oh, okay. You're talking about passive reference configuration? Yes, yes. Current will always go from high to low. Yes. Yes.
So back to the diagram that we're looking at right now.
Uh-huh.
This is the reverse bias, right? So this would be this part. Where